Hey guys, welcome to your very first flipped lesson. Make sure you have pencil and paper, that way you can follow along as we get through this video. Okay. Much of mathematics and science is developed when people recognize and describe patterns. In this course, we're going to start by taking a look at visual patterns and number patterns and see if we can predict what might come next based on that pattern. Let's get started with playing a short game. Here we have a visual pattern. We have three different figures and something changes from one figure to the next. Let's see if you can take time to identify what pattern is occurring as we advance to the next figure. How'd you do? Hopefully you were able to notice that we were adding the same set of three blocks every single time we progress to a new figure. Here's the next one. Let's see if you can take some time to identify what's happening as we move from one figure to the next. Then use that to make a prediction as to what figure 4 might look like. How'd you do? Hopefully you noticed that we were adding one block to the top, one block to the back, and one block to the right side every single time. Here's our next visual pattern. Can you identify what happens as we move from one figure to the next and use that to make a prediction? How'd you do? Hopefully you noticed a new row was being added on the bottom of that figure every time, and there was one cup added to that row. Here's our last visual pattern of the day. Now this one is a little bit more complicated, so go ahead and take some time to make a prediction as to what that third figure might look like based on how stack 1 changed to stack 2. How did you do? This one was a little bit more challenging, but hopefully you realized there was almost like a plus-like shape of blocks being added at each level. And there was an additional block added to each side of that plus sign every single time. Now these are visual patterns that we've been looking at, but we can also look at number patterns. Here's our first number pattern. Can you identify how this changes from one number to the next? Once you have identified that, let's use that to predict what might come next. How did you do? Hopefully you noticed that each time we move from one number to the next, we were multiplying by the number 4. Based on this pattern, we could identify what the next number would be by taking 64 and multiplying it by 4. Let's do one more example. This one is a little bit trickier than the previous one, so I encourage you to pause the video and take some time to think this one through to make your prediction. Like I said, this one was trickier, but how did you do? Let's see if we can figure out what pattern was occurring. To get from -5 to -2, I noticed that we're adding 3. To get from -2 to 4, it looks like we're adding 6. And to get from 4 to 13, it looks like we are adding 9. Notice it looks like we are adding 3 additional numbers every single time. Based on this pattern, to get from here to the next figure, we must be adding 12. What we just did was a series of using the inductive reasoning process. Now, inductive reasoning is something you're going to want to add to your notes. This is the process of looking for patterns and making conjectures, or basically guesses. We don't know if it's true, but based on a pattern, we make a conjecture. Now, there are 3 helpful steps that we follow when using inductive reasoning. Okay, we found a pattern like we did in the previous examples. Based on that pattern, we made a conjecture. And some of those, our conjecture was that we were adding 3 each time. The very final step of inductive reasoning is to verify the conjecture. Okay, today we're going to focus on steps 1 and 2, and later on in the semester we're going to hit step 3 very hard. Let's take a look at this. Making a conjecture. In order to make a conjecture, you must examine several examples. Okay, these examples are going to help you identify a pattern. Then once you know a pattern, you can write out a conjecture. So as you see on the screen, the conjecture we're looking at says that the sum of the first n positive integers is blank. Now, right now, this might be hard to think through, but that's why looking at several examples is going to help us think this through in order to fill in the blank. So, the sum of the first n positive integers. Well, let's just look at one positive integer. Okay, the sum of 1 plus nothing is just 1. Let's take a look at the sum of the first 2 odd positive integers. The first 2 odd positive integers are 1 and 3. The sum of 1 and 3 is 4. Okay, let's look at another example. The sum of the first 3 odd positive integers. So 1 plus 3 plus 5 equals 9. Let's do one more example just so we can be sure that we're actually picking up on a pattern. So let's look at the sum of the first 4 odd positive integers. 1 plus 3 plus 5 plus 7 is going to give us 16. Now, we have to take a moment to see if we're identifying some sort of pattern. What I'm noticing right now is that all of these answers look like they are perfect squares. So let's represent them as perfect squares. I could represent this as 1 to the power of 2. I could represent 4 as 2 to the power of 2. I could represent this as 3 to the power of 2. And I could represent this as 4 to the power of 2. Okay, I'm going to write that down here because it's not working on my screen. So now, let's see. This example, we were just looking at n equals 1. So when n equals 1, this was giving us n squared. In this case, we had n equals 2. Now notice, this is also n squared. In this example, n was equal to 3. Now notice we still have n squared. Based on the pattern that we just identified, I feel comfortable filling in n squared to our statement. Now today we're not going to work on proving our conjectures, but we are just going to work on identifying patterns and making conjectures. Okay? We are going to look at how to disprove a conjecture, which brings me to my next slide called counterexamples. Counterexamples is an example that shows a conjecture is false. So let's take a look at this conjecture and see if we can find a counterexample. For all real numbers x, the expression x squared is greater than or equal to x. So let's look at an example. What if I say x equals 2? All right, the expression x squared, so that would be 2 squared, which is 4, is greater than or equal to x. Well, of course, 4 is greater than or equal to x in this case. Let's look at another example. What if we said x equals 3? 3 squared equals 9. Well, 9 is greater than x. So these two examples are kind of proving the statement's true, but can we come up with a value of x that disproves this statement? Now let me highlight something important here. This says real numbers. We have to know what real numbers are. Real numbers are any number negative to positive. They could be fractions, they could be decimals. So let's consider maybe a decimal option here. What if I were to let x equal 0.5? Now let's go ahead and take 0.5, raise it to the power of 2. You can either use mental math or your calculator to check, but when you raise that to the power of 2, you get 0.25. Now notice, this is not greater than x squared. So what we have found is we have found a counter example. The counter example was x equals 0.5. This is an example that disproves this conjecture. Okay? All right, so here we have a German mathematician called Christian Goldbach. He's famous for his conjecture. Okay, his famous conjecture is that every even number greater than 2 can be written as the sum of 2 primes. Okay, now remember, prime numbers are numbers that can only be divisible by 1 in itself. So 1 is a prime number, 2 is a prime number, 3 is a prime number, 5 is a prime number, 7, and we could continue this list if we wanted to. Now, his conjecture has never been disproven, but it's also never been proven formally. However, it is worth noting that it has been proven up to the number 4 times 10 to the 14th. Now, this is scientific notation. Just as a reminder, because we will see scientific notation as we move out throughout the semester, what does that number mean? In order to find that number, which is super, super large, we start with the number 4, which has a decimal point here, and we move that decimal point 14 times to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm running out of room. This number is huge, which is why it's represented in scientific notation. Okay, so although Goldbach's conjecture hasn't been proven for every number, it has been proven for every number up to this huge number that we see on the board. So one takeaway from this conversation is to remember, just because you prove something is true for several specific cases does not prove that it is true in general. But I do want you to know that we will learn how to prove conjectures later in this course. It's just not a focus for today. Here's our very last example of the day. I wanted to give you a real life example or a real world example. Go ahead and read the information that's in that box. See if you can look for a pattern and make a conjecture. Once you've done that, I will verify whether your conjecture is true or false. Okay, verifying the conjecture. Hopefully you noticed that a full moon was occurring every 29 to 30 days. If you picked up on this pattern and made that conjecture, it is actually true. A simple internet search will show you that the moon revolves around the earth once approximately every 29.5 days, which is why we only see the full moon every 29 to 30 days. Before we end the lesson, I just want to review a few items that should be written down on your notes for today. What is a conjecture? What is inductive reasoning? And what is a counterexample? I look forward to seeing you guys in class tomorrow. Bye.